Welcome back in, everybody. My name is Michael. Hope you're having a wonderful day so far. Today we're going to be jumping back into Introductions to Algorithms Chapter 4. This is the 4th edition by CLRS, more specifically Chapter 4.4, the recursion tree method for solving recurrences, and Chapter 4.5. We're going to be reading these two sections today, and it should be a good little study session. 4.4, the recursion tree method for solving recurrences. Although you can use the substitution method to prove that a solution to a recurrence is correct, you might have trouble coming up with a good guess. Drawing out a recursion tree, as we did in our analysis of the merge sort recurrence in section 2.3.2, can help. In a recursion tree, each node represents the cost of a single subproblem somewhere in the set of recursive function invocations. You typically sum the costs within each level of the tree to obtain the per level costs, and then you sum all of the per level costs to determine the total cost of all levels of the recursion. Sometimes, however, adding up the total cost takes more creativity. A recursion tree is best used to generate intuition for a good guess, which you can then verify by the substitution method. If you are meticulous when drawing out a recursion tree and summing the costs, however, you can use a recursion tree as a direct proof of a solution to a recurrence. But if you use it only to generate a good guess, you can often tolerate a small amount of sloppiness, which we can simplify the math. When you verify your guess with the substitution method later on, your math should be precise. This section demonstrates how you can use recursion trees to solve recurrences, generate good guesses, and gain intuition for recurrences. An illustrative example. Let's see how a recursion tree can provide a good guess for an upper bound solution to the recurrence of t of n equals to 3t of n over 4 plus theta n squared. Figure 4.1 shows how to derive the recursion tree for t of n equals to 3t n over 4 plus cn squared, where the constant c is greater than 0, is the upper bound constant in the theta n squared term. Part A of the figure shows t of n, which part B expands into an equivalent tree representing the recurrence. The cn squared term at the root represents the cost at the top level of the recursion, and the three subtrees of the root represents the costs incurred by the subproblems of size n over 4. Part C shows the process carried one step further by expanding each node with cost t of n over 4 from part B. The cost for each of the three children of the root is c of n over 4 squared. We continue expanding each node in the tree by breaking it into its constituent parts as determined by the recurrence. Because problem sizes decrease by a factor of 4 every time we go down by one level, the recursion must eventually bottom out in a base case where n is less than n naught. By convention, the base case is t of n equals to theta of 1, where n is less than n naught, and where n naught is greater than 0. Is any threshold constant sufficiently large that a recurrence is well defined? For the purpose of intuition, however, let's simplify the math a little. Let's assume that n is an exact power of 4, and the base case is t of 1 equals to theta of 1. As it turns out, these assumptions don't reflect the asymptotic solution. What's the height of the recursion tree? The subproblem size for a node at depth I is n over 4 to the power of I. As we descend the tree from the root, the subproblem size hits a n equals 1 when n over 4 to the power of I equals to 1, or equivalently when I equals to log base 4 of n. Thus, the tree has internal nodes of depths 0, 1, 2, all the way up to log base 4 n minus 1, and leaves at depth log base 4 of n. Part D of figure 4.1 shows the cost at each level of the tree. Each level has 3 times as many nodes as the level above, and so the number of nodes at each depth is I is 3 to the power of I. Because subproblem size reduced by a factor of 4 for each level further from the root, each internal node at depth I equals 0, 1, 2, all the way to log base 4 n minus 1 has a cost of c times n over 4 to the power of I squared. Multiplying, we see the total cost of all nodes at a given depth I is 3 to the power of I times c of n over 4 to the power of I squared, which reduces down to 3 over 16 to the power of I times c times n squared. The bottom level at depth log base 4 times n contains 3 to the power of log base 4 times n, which equals to n to the power of log base 4 times 3, leaves using equation 3.21 on page 66. Each leaf contributes theta of 1, leading to a total leaf cost of theta of n log base 4 times 3. We add up the cost over all the levels to determine the cost of the entire tree. We've derived the guess of t of n equals to O of n squared for the original recurrence. In this example, the coefficients of c times n squared form a decreasing geometric series. By equation a dot 7, the sum of these coefficients is bounded from above by the constant 16 over 13, since the root's contribution to the total cost is cn squared. The cost of the root dominates the total cost of the tree. In fact, if O(n) squared is indeed an upper bound for the recurrence, as we'll verify in a moment, then it must be a tight bound. Why? The first recursive call contributes a cost of theta n squared, and so omega n squared must be a lower bound for the recurrence. Let's now use the substitution method to verify that our guess is correct, namely that t of n is equal to big O of n squared is an upper bound for the recurrence, t of n equals to 3t n over 4 plus theta n squared. We want to show that t of n, which is less than or equal to d times n squared for some constant d, which is greater than 0. Using the same constant c greater than 0 as before, we have this, where we prove that t of n is less than or equal to d times n squared. Where the last steps holds if we choose d of greater than or equal to 16 over 13 times c. For the base case of the induction, let n not be greater than 0, be a sufficiently large threshold constant that the recurrence is well defined when t of n is equal to theta of 1 for n less than n naught. We can pick d large enough that d dominates the constant hidden by the theta, in which case d n squared is greater than or equal to d, which is greater than or equal to theta of n, for 1, which is less than or equal to n, which is less than n naught, completing the proof of the base case. The substitution proof we just saw involves two named constants, c and d. We named c and used it to stand for the upper bound constant hidden and guaranteed to exist by the theta notation. We cannot pick c arbitrarily, it's given to us, although for any such c, any constant c prime which is greater than c or equal to c also suffices. We also named d, but we were free to choose any value for it that fit our needs. In this example, the value of d happened to depend on the value of c, which is fine, since d is a constant if c is a constant. Okay, an irregular example. Let's find an asymptotic upper bound for another more irregular example. Figure 4.2 shows the recurrence tree for the recurrence of t of n, which is equal to t of n over 3 plus t of 2n over 3 plus theta n. This recursion tree is unbalanced, with different root-to-leaf paths having different lengths. Going left at any node produces a subproblem of 1/3 of the size, and going right produces a subproblem of 2/3 the size. Let n naught be greater than 0, the implicit threshold constant that t of n is equal to theta of 1 for 0, which is less than n, which is less than n naught. And let c represent the upper bound constant hidden by the theta n term for n greater than or equal to n naught. There are actually two n naught constants here, one for the threshold in the recurrence and the other for the threshold in the theta notation. So we'll let n naught be the larger of the two constants. Okay, so we start off with some bound of c of n, right? We divide each left-hand subproblem into n over 3, and we divide the right-hand subproblem in a recursive 2n over 3. Each of these has a cn total running time bound, right? The height of the tree runs down the right edge of the tree, corresponding to the subproblems of size n, 2 over 3n, 4 over 9n, all the way up to theta of 1, with cost bounded by c of n, c 2n over 3, c 4n over 9, up to theta of 1, respectively. We hit the rightmost leaf when 2 over 3 to the power of h, n is less than n naught, which is less than or equal to 2 over 3 h minus 1 n, which happens when h is equal to the floor value of log base 3 over 2 of n over n naught plus 1. Since applying the floor bounds in equation 3.2 on page 64 with x equals to log base 3 over 2, since applying the floor bounds in equation 3.2 on page 64 with x equals to log base 3 over 2 of n over n naught, we have 2 over 3 to the power of h times n equals 2. Thus, the height of the tree is h equals to theta log n. We are now in a position to understand the upper bound. Let's postpone dealing with leaves for a moment, summing the cost of internal nodes across each level. We have at most Cn per level times the theta log n tree height for a total cost of big O of n log n for all internal nodes. It remains to deal with the leaves of all the recursion tree, which represent base cases, each costing theta of 1. How many leaves are there? It's tempting to upper bound their number by the number of leaves in a complete binary tree of height equals to h of the floor log base 3 over 2 of n over n naught plus 1, since the recursion tree is contained within such a complete binary tree. But this approach turns out to give us a poor bound. The complete binary tree has one node at the root, two nodes at depth 1, and generally 2 to the power of k nodes at depth k. Since the height is equal to the floor of log base 3 over 2 n plus 1, there are this many leaves in the complete binary tree, which is an upper bound of the number of leaves in the recursion tree. Because the cost of each leaf is theta of 1, this analysis says that the total cost of all leaves in the recursion tree is big O n to the power of log base 3 over 2 squared, which is equal to, or big O of n to the power of 1.71, which is an asymptotically greater bound than the big O of n log n cost of all internal nodes. In fact, as we're about to see, this bound is not tight. The cost of all leaves in the recursion tree is big O of n, asymptotically less than big O of n log n. In other words, the cost of all the internal nodes dominates the cost of the leaves, not vice versa. Rather than analyzing the leaves, we could quit right now and prove by substitution that T of n is equal to theta of n log n. This approach works, see exercise 4.4-3, but it's instructive to understand how many leaves this recursion tree has. You may see recurrences for which the cost of leaves dominate the cost of internal nodes, and then you'll be in better shape if you've had some experience analyzing the number of leaves. To figure out how many leaves there are, let's write a recurrence L of n for the number of leaves in the recursion tree for T of n. Since all the leaves in T of n belong either to the left subtree or the right subtree of the root, we have this, L of n, which is equal to 1 if n is less than n naught, or L of n over 3 plus L of 2n over 3 if n is greater than or equal to n naught. This recurrence is similar to recurrence 4.14, but it's missing the theta of n term, and it contains an explicit base case. Because this recurrence omits the theta n term, it is much easier to solve. Let's apply the substitution method to solve that it has a solution of L of n equals to big O of n. Using the inductive hypothesis, L of n less than or equal to d of n for some constant d greater than 0, and assuming that the inductive hypothesis holds for all values less than n, we have L of n, which is equal to L of n over 3 plus L of 2n over 3, which is less than or equal to d times n over 3 plus 2 times d times n over 3, which is less than or equal to d times n, which holds for any d greater than 0. We can now choose d large enough to handle the base case ln equals to 1 for 0, which is less than n, which is less than n naught, for which d is equal to 1 suffices, thereby completing the substitution method for the upper bound on leaves. Exercise 4.4-2 asks you to prove that L of n equals to theta of n. Returning the recurrence 4.14 for T of n, it now becomes apparent that the total cost of leaves over all levels must be L of n times theta of 1, which is equal to theta of n. Since we have derived the bound of big O n log n on the cost of the internal nodes, it follows that the solution to recurrence 4.14 is T of n equals to big O of n log n plus theta n, which is equal to big O of n log n. Exercise 4.4-3 asks you to prove that T of n equals to theta n log n. It's wise to verify any bound obtained with the recursion tree by using the substitution method, especially if you've made simplifying assumptions. But another strategy altogether is to use more powerful mathematics, typically in the form of the master method in the next section, which unfortunately doesn't apply to recurrence 4.14 or the Acrobasi method, which does but requires calculus. Even if you use a powerful method, a recursion tree can improve your intuition for what's going on beneath the heavy math. The master method provides a cookbook method for solving algorithmic recurrences of the form of t of n equals to a times t of n over b plus f of n, where a is greater than 0 and b is greater than 1 are constants. We call f of n a driving function, and we call a recurrence of this general form a master recurrence. To use the master method, you need to memorize 3 cases, and then you'll be able to solve any master recurrences quite easily. A master recurrence describes the running time of a divide and conquer algorithm that divides a problem of size n into a subproblems, each of size n over b, which is less than n. The algorithm solves the a subproblems recursively, each in t of n over b time. The driving function, f of n, encompasses the cost of dividing the subproblem before the recursion, as well as the cost of combining the results of the recursive solutions to subproblems. For example, the recursion arising from Strasson's algorithm is a master recurrence with a equals to 7 and b equals to 2. A driving function, f of n, equals to big theta n squared. As we have mentioned in solving recurrences that describe the running time of an algorithm, one technicality that we'd often prefer to ignore is the requirement that the input size n be an integer. For example, we saw that the running time of merge sort can be described by recurrence 2.3, t of n equal to 2t of n over 2 plus theta n on page 41. But if n is an odd number, we really don't have 2 problems of the exact half of the size. Rather, to ensure that the problem sizes are integers, we round one subproblem down to the floor of n over 2 and the other up to the size ceiling of n over 2. So the true recurrence is t of n equals to t of the ceiling n over 2 plus t of the floor n over 2 plus theta n. But this floor and ceilings recurrence is longer to write and messier to deal with in recurrence 2.3, which is defined on the reals. We'd rather not worry about floors and ceilings if we don't have to, especially since the 2 recurrences have the same big theta n log n solutions. The master method allows you to state a master recurrence without floors and ceilings implicitly and implicitly infer them. The master method allows you to state a master recurrence without floors and ceilings and implicitly infer them. No matter how the arguments are rounded up or down to the nearest integer, the asymptotic bounds that it provides remain the same. Moreover, as we'll see in section 4.6, if you define your master recurrence on the reals without implicit floors and ceilings, the asymptotic bounds still don't change. Thus, you can ignore floors and ceilings for master recurrences. Section 4.7 gives sufficient conditions for ignoring floors and ceilings in more general divide and conquer recurrences. So the master theorem. The master method depends upon the following theorem. Theorem 4.1, master theorem. Let a be greater than 0 and b greater than 1 be constants, and let f of n be a driving function that is defined and non-negative for all sufficiently large reals. Define the recurrence t of n on n which is in the values of n by t of n equals to a t of n over b plus f of n, where a times t of n over b actually means that a prime t of the floor of n over b plus a double prime t of the ceiling of n over b for some constants a prime which is greater than 0 and a double prime which is greater than or equal to 0, satisfying the a equals to a prime plus a double prime. Then the asymptotic behavior of t of n can be characterized as follows. 1. If there exists a constant that is greater than 0 such that f of n is big O of n to the power of log base b a minus said constant, then t of n equals to big theta n to the power of log base b times a. If there exists a constant k greater than or equal to 0 such that f of n is equal to big theta n to the power of log base b times a times log to the power of k times n, then t of n is equal to big theta n to the power of log base b times a times log to the power of k plus 1 times n. If there exists a constant that is greater than 0 such that f of n is equal to big omega of n to the power of log base b times a plus said constant, and if f of n additionally satisfies the regularity condition a times f of n over b, which is less than the constant c times f of n for some constant c less than 1 and all sufficiently large n, then T of n is equal to big theta f of n. Before applying the master theorem to some examples, let's spend a few moments to understand broadly what it says. The function n to the power of log base b times a is called the watershed function. In each of the three cases, we compare the driving function f of n to the watershed function n to the power of log base b times a. Intuitively, if the watershed function grows asymptotically faster than the driving function, then case 1 applies. Case 2 applies if the two functions grow at nearly the same asymptotic rate. Case 3 is the opposite of the case 1, where the driving function grows asymptotically faster than the watershed function, but the technical details matter. In case 1, not only must the watershed function grow asymptotically faster than the driving function, it must grow polynomially faster. That is, the watershed function n to the power of log base b times a must be asymptotically larger than the driving function f of n by at least a factor of big theta to the power of that constant, for some constant epsilon that is greater than. The master theorem then says that the solution is T of n, which is equal to big theta n to the power of log base b times a. In this case, if we look at the recursion tree for recurrence, the cost per level grows at least geometrically from the root to leaves, and the total cost of leaves dominates the total cost of the internal nodes. In case 2, the watershed and driving functions grow at nearly the same asymptotic rate, but more specifically, the driving function grows faster than the watershed function by a factor of big theta of log to the power of k times n, where k is greater than or equal to 0. The master theorem says that we take on an extra log n factor of f of n, yielding the solution T of n equals to big theta n to the power of log base b of a times log to the power of k plus 1 times n. In this case, each level of the recursion tree costs approximately the same, big theta n to the power of log base b times a times log to the power of k times n, and there are big theta log n levels. In practice, the most common situation for case 2 occurs when k is equal to 0, in which case the watershed and driving functions have the same asymptotic growth, and the solution is T of n equals to big theta n to the power of log base b times a times log n. Case 3 mirrors case 1. Not only the driving function grows asymptotically faster than the watershed function, but it grows polynomially faster. That is, the driving function, f of n, must be asymptotically larger than the watershed function by n to the power of log base b times a, by a factor of big theta n to the power of e for some constant e greater than 0. Moreover, the driving function must satisfy the regularity condition that a times the f of n over b, which is less than c times f of n. This condition is satisfied by most of the polynomial bounded functions that you are likely to encounter when applying case 3. The regularity condition might not be satisfied if the driving function grows slowly in local areas, yet relatively quick overall. Exercise 4.5 through 5 give an example of such functions. For case 3, the master theorem says that the solution is T of n equals to big theta of f of n. If we look at the recursion tree, the cost per level drops at least geometrically from the root to the leaves, and the root costs dominate the cost of all other nodes. It's worth looking again at the requirement that there be polynomial separation between the watershed function and the driving function in either case 1 or case 3 to apply. The separation does not need be much, but it must be there, and it must grow polynomially. For example, for the recurrence of T of n equals to 4 of T n over 2 plus n to the power of 1.99, admittedly not a recurrence you're likely to see when analyzing an algorithm, the watershed function is n to the power of log base b times a, which is equal to n to the power of 2. Hence, the driving function, f of n equals to n 1.99, is polynomially smaller than the factor of n to the power of 0.01. Thus, case 1 applies with a constant value of 0.01. Using the master method. To use the master method, you determine which case, if any, of the master theorem applies and write down the answer. As a first example, consider this recurrence. For this recurrence, we have a equal to 9 and b equal to 3, which implies that the watershed function is big theta of n squared. Since f of n is equal to big O of n to the power of 2 minus some constant for any constant less than or equal to 1, we can apply case 1 of the master theorem to conclude that the solution is T of n equals to big theta n squared. That was a lot easier than before, right? Now consider the recurrence this, which has a equals to 1 and b equals to 3 over 2, which means that the watershed function is equal to n to the power of 0, which is 1. Case 2 applies since f of n is equal to 1, and which equals to big theta is equal to 1, or big theta of 1. Case 2 applies since f of n is equal to 1, which is equals to big theta n to the power of log base b times a times log to the power of 0 times n, which is equal to big theta of 1. The solution to the recurrence is t of n equals to big theta log n. For the recurrence of t of n equals to 3 times t n over 4 plus n log n, we have a equals to 3 and b over 4, which means that the watershed function is big O of n to the power of 0.793. Since f of n is equal to n log n, and big omega equals to n log base 4 of 3 plus some constant, where some constant can be as large as approximately 0.2, case 3 applies as long as the regularity condition holds for f of n. It does because for sufficiently large n, we have that a times f of n over b is equal to 3 n over 4 log n over 4, which is less than 3 over 4 times n log n, which is equal to c times f of n for some constant c, which is equal to 3 over 4. By case 3, the solution to the recurrence is t of n, which is equal to big theta n log n. Now let's look at this recurrence, where 2 times t of n over 2 plus n log n, where we have a equals to 2 and b equals to 2, a watershed function equals to n, and case 2 applies. Since f of n is equal to n log n, big theta, the watershed function, equals to the log to the power of 1 times n. We conclude that the solution is big theta n log squared times n. We can use the master method to solve the recurrences we saw in sections 2.3.2, 4.1, and 4.2. Recurrence 2.3, which is this, on page 41, characterizes the running time of merged sort. Since a is 2 and b is 2, the watershed function is n. Case 2 applies because f of n is equal to big theta of n, and the solution is t of n equals to big theta n log n. The recurrence 4.9, t of n is equal to this, on page 84, describes the running time of the simple recursive algorithm for matrix multiplication. We have a equals to 8 and b equals to 2, which means that the watershed function is n to the power of log b of a, which is equal to n cubed. Since n cubed is polynomially larger than the driving function, f of n, which is equal to big theta of 1, indeed we have f of n equals to big O of n to the power of 3 minus some constant for any positive constant less than 3, case 1 applies. We conclude that t of n is equal to big theta n cubed. Finally, recurrence 4.10, t of n equals to 7t of n over 2 plus big theta n squared, on page 87, arose from the analysis of Strasson's algorithm for the matrix multiplication. For this recurrence, we have a equals to 7 and b equals to 2, and the watershed function is n to the power of log b a, which is equal to n to the power of log 7. Observing that log 7 equals to 2.8, we can let e equal to 0.8, and the bound of the driving function be f of n equals to big theta n squared, which is equal to big O, which is equal to big O n to the power of log 7 minus e. Case 1 applies with the solution t of n equals to big theta n to the power of log 7. When the master method doesn't apply, there are situations where you can't use the master theorem. For example, it can be that the watershed function and the driving function cannot be asymptotically compared. We might have that f of n is much greater than the watershed function for an infinite number of values of n, but also that f of n is much less than the watershed function for an infinite different number of values of n. As a practical matter, however, most of the driving functions that arise in the study of algorithms can be meaningfully compared with the watershed function. If you encounter a master recurrence for which that's not the case, you'll have to resort to the substitution or other methods. Even when the relative growths of the driving and watershed functions can be compared, the master theorem does not cover all the possibilities. There is a gap between cases 1 and 2 when f of n is equal to little o of the watershed function. Yet the watershed function does not grow polynomially faster than the driving function. Similarly, there is a gap between cases 2 and 3 when f of n is equal to little omega of the watershed function, and the driving function grows more than polylogarithmically faster than the watershed function, but it does not grow polynomially faster. If the driving function falls into one of these gaps, or if the irregularity condition in case 3 fails to hold, you'll need to use something other than the master method to solve the recurrence. As an example of a driving function falling into a gap, consider the recurrence t of n equals to 2t of n over 2 plus n over log n. Since a is equal to 2 and b equals to 2, the watershed function is equal to this, which reduces down to n. The driving function is n over log n, which is little o of n, which means that it grows asymptotically more slowly than the watershed function of n. But n over log n grows only logarithmically slower than n, not polynomially slower. More precisely, equation 3.24 on page 67 says that log n is equal to little o of n to the power of some constant for any constant epsilon greater than 0, which means that 1 over log n is equal to little omega of n to the power of epsilon, and n over log n is equal to little omega of n to the power of 1 minus epsilon, which is equal to little omega of n to the power of log base b of a minus epsilon. Thus, no constant epsilon greater than 0 exists such that n over log n equals to big O of n to the power of log base b of a minus epsilon, which is required for case 1 to apply. Case 2 fails to apply as well, since n over log n is equal to big theta of n to the power of log base b of a times log to the power of k times n, where k is equal to -1, but k must be non-negative for case 2 to apply. To solve this kind of recurrence, you must use another method, such as the substitution method, section 4.3, or the Acrobazi method in section 4.7. Exercise 4.6-3 asks you to show that the answer is big theta of n log n. Although the master theorem doesn't handle this particular recurrence, it does handle the overwhelming majority of recurrences that tend to arise in practice.